Okay, chemistry 1411. Here we are in section 12.3 of chapter 12, of course, and this is dealing with rate laws. And if we back up one slide to the last slide that we looked at during the first lecture, we talked about the effect of concentration on a reaction. And I said, you know, the bottom line is what's shown here, which is that as concentration increases, collision frequency is going to increase, and thus reaction rate increases. So as we have a higher concentration, our rate is going to increase. And I said it's related to something called a rate law that I have here in this box right here, but I didn't explain what a rate law is. And again, a rate law is nothing more than a relationship between the instantaneous rate of a reaction and the concentration of the reactants. Okay, so only the reactants. Now, if we have, for example, and this is just an example, if we have a generic reaction like this, A plus B gives you C and D, and we have the stoichiometric coefficients here, the rate law would be written like this. We have our rate, okay, which is going to be equal to K, and this K is called the rate, this is called the rate constant, multiplied by the concentration of A to an exponent X and the concentration of B to an exponent Y. So our rate is equal to rate constant times the concentration of our reactants to specific coefficients. Now, it's important that you note that X and Y are not, and I have this in my notes, are not stoichiometric coefficients. These are not the coefficients from the reaction. Another thing that's important to notice is that this K is lowercase. This is a lowercase k because later on we're going to look at uppercase K, and the big K, we call that an equilibrium constant. So that's another chapter. That's going to be in chapter 13, so you don't really have to be too concerned with that right now, the big K. So we have a little k, which is our rate constant, and X and Y are not the stoichiometric coefficients. They have nothing to do with A and B. They could be the same numbers as A and B, but that would only be coincidental if that was to happen. Let's move on. It says the exponents, X and Y, indicate how the rate of the reaction varies in response to the concentration of those two reactants. Now, where do we get X and Y from? If you're like, where do those numbers come from? Well, we have to determine those numbers by an experiment. We have to do some kind of experiment, and by an experiment, we can evaluate what those numbers are. I'm going to show you how to do that today. Now, what numbers can X and Y be? They can be a whole plethora of numbers. They can be zero, they can be positive, they can be negative, they can even be fractions. Okay, we're not going to deal with a lot of fractions, but we will look at a specific example today where we will look at a fraction. Anyhow, what about the rate? It says the rate must be defined as the appearance or disappearance of a chemical species in a reaction, right? This is a review from last class, right? This is something that we looked at during the last lecture. Well, let's move on and let's talk a little bit more about rate laws. Going back to our generic equation here. Now, this is just for example, okay? Just an example. This doesn't happen all the time, but for example, let's say we had this reaction that we're interested in. It says the rate law for this reaction has been experimentally determined to be rate is equal to K, the rate constant, times A to the power of 2 and B to the power of 1, where rate is measured as the disappearance of B. It says when we have a 1 as our exponent, we say that the reaction is first order with respect to B. So where does this first order come from? It comes from the number 1. And we say that it's second order with respect to A. So since A is to the power of 2, we say it's second order. Now, the overall order of the reaction is just the sum of those exponents. So if we take 2 plus 1, we get 3. So we say the reaction is overall third order. So again, what we're looking at is this rate law right here. We say second order in A, first order with respect to B, and overall, it's third order. Now, the rate constant is constant for a given temperature. It's important that you always keep that in mind, that rate constant K, small k, can change. It will change with temperature. Something else you might be asking are, what would the rates, or what would the units, of K be? Well, the units of K are going to depend, won't they? Because if we rearrange the generic equation that we had before, on the previous slide, which was rate is equal to K times A to the power of X times B to the power of Y. If we solve this for K, we get that K is equal to rate divided by A to the power of X times B to the power of Y. So that means that K is going to be dependent on these exponents here. So that means the units of K will vary depending on the situation, depending on the reaction order. Well, with that in mind, let's take a look at an example where we're going to determine the units of a rate constant. It says here, asks us to determine the units of the rate constant. So remember, small k is the rate constant. Determine the units of the rate constant in the following rate law if the rate is measured in units of molarity per minute. So moles per liter per minute. Okay, that's what m times m to the reciprocal, or m to the power of -1 is. Okay, so moles per liter per minute. Anyhow, so I'm just going to write it down a little bit more, or a little bit bigger here, because I just need it that way. Anyhow, so we have k times a to the power of 1/2 times b squared, or to the power of 2. So that means that the overall reaction order here is going to be what? 1/2 plus 2. So that's 2.5, right? So we have a fraction here. So our first example involves a fraction. Another way we could say this is we could say our rate, which is in moles per liter per minute, is equal to K times the concentration of A, which is going to be in molar, right? Remember, big M equals moles per liter to the power of 1/2 times the concentration of B, which will also be in molarity, squared. So what do we do when we have two exponents on two numbers that we're going to multiply? We add those exponents, don't we? Okay, so again, I'm not going to reteach algebra, but that's what we have to do. So we have molarity times minutes to the -1 is going to equal K times M to the power of 5/2, right? 1/2 plus 2 equals 5/2. I'm expressing it as a fraction, okay? So you should know how to add numbers together. Anyhow, so now we're going to solve for our K. So we're going to say K is going to be equal to moles per liter per minute divided by molarity to the power of 5/2. Well, if we take 1 and we subtract 5/2, what do we get? We get that our K, our K is going to be equal to what? Moles to the -3/2 per minute. And so those are the units of our K. Again, I'm just doing the simple math in my head. If you take 1 and you subtract 5/2, you get -3/2, like that. So just a little bit of mental math. I'm going to do a lot of algebra and little bits of math in my head in this class. So those are the units of our K. Our K is in units of moles to the power of -3/2 per minute. Okay, now we're mostly going to be concerned with reactions that are first, second, and zero order. We're not going to be dealing with a ton of what would this be? So it'd be 5/2 order. We're not going to deal with that a whole lot. But the idea is that we should always be able to evaluate the units of K. Give me a thumbs up if you're like, yeah, heck yeah, I can determine the value of K. No problem. Just give me the order of the reactants, and sure, I can figure it. Great. Awesome. All right. Well, let's move on from there. Now, if we look at the order for a reaction, if we look at overall reaction order, so if we have a reaction that is zero order, okay? So if we have, for example, rate is equal to K times the concentration of A to the power of 0, well, this is going to cancel out, and that means that rate is simply going to be equal to K. So if rate is in moles per liter per second, well, then K would have to be in moles per liter per second, wouldn't it? Okay, if you have a reaction that's first order, so if you had rate is going to be equal to K times A to the power of 1, right, first order, well, in that case, if A is in moles per liter, that means that in K would have to be per seconds, right? Seconds to the -1 in order for rate to be moles per liter per second. Okay, if you had a second order reaction, rate is equal to K times A to the power of 2. Well, in that case, the units of K would have to be liter moles reciprocal times second reciprocal. We could also define this as moles to the -1 times seconds to the -1. Okay, and if you had a third order reaction, so rate is equal to K times A to the power of 3, then you'd have moles to the -2 times seconds to the -2. So that's just, me writing it down like that. So you see that what all of these K units have in common, what do they have in common? They all have seconds to the -1. And what changes is this part over here. Now there is a kind of a shorthand you can take. You can say, well, if it's third order, then it's going to be the negative of 1 less, right? So it's always the negative of 1 less. Anyhow, I mean, if you have 1 less than 1, you have 0, so there's no negative, so there's no molar. Anyhow, that's kind of a shorthand that you can use, but I think it's just as expedient to determine the units of rate constant. All right, anyhow, so the order with respect to a reactant tells us the dependence of the reaction rate on the concentration of that particular reactant. All right, and the overall order gives us some kind of understanding how all the reactants are going to contribute to the rate of the reaction. A student asked in the chat, says, in an exam, will we be given the exponents in order to figure out problems like this, or is there a way to determine the exponents? Yes, there is definitely a way to determine reaction order. We use what's called the method of initial rates, which is something that we're going to look at today. Again, let me remind you, I highly recommend that everybody reads the entire chapter before coming to class so that you know what's coming up, okay? This class is a really difficult class if you just come to class without having read the chapter ahead of time. Anyhow, let's take a look at a practice problem here. It says we have this specific reaction, 2 ICl plus H2 gives us I2 plus 2 HCl. We're given the rate, okay? We're given the rate of reaction is equal to K times the concentration of ICl to the power of 1 times H2 to the power of 1. So this is a second order reaction overall. You're like, how did you get that, Mr. Dion? Well, think, this is first order and this is first order, right? When we don't have any exponent, we know it's a number 1. 1 plus 1 is 2. All right, so we have a second order reaction. It says the value of the rate constant has a value of molar to the -1 times seconds to the -1. And it asks us to calculate the rate of appearance of iodine when we have the concentration of the two reactants as being 0.25 molar. So I'm on the first part right here. Well, they're telling us that the rate, okay, the rate is measured as the rate of appearance of iodine, I2. So that means the rate is going to be delta, the change in concentration of I2 over the change in time, which is equal to K times ICl times H2. Well, if we're trying to calculate the rate of appearance of I2, which is this, and we have the two concentrations, and we also have the rate constant, this is just kind of what I call a plug and chug question, right? We just plug the numbers in, and there we go. We have the answer. So let's try plugging some numbers in. So we get that the rate of appearance of our iodine over time is going to be equal to K, which is 1.63 times 10 to the -1 molar to the -1 seconds to the -1 multiplied by the concentration of both of these. And you see that they're both 0.25. So I'm just going to write 0.25 times 0.25. I could have written 0.25 squared. Either, I left my units out. That's not good. So we have 0.25. I'll just put squared like that. All right. So that's going to be equal to 1.63 times 10 to the -1 molar to the -1 seconds to the -1 multiplied by 0.0625 molar squared. And if we take molar squared and we multiply by molar to the -1, you add 2 plus -1, what do you get? 1. So that means that our rate, the change in the concentration of iodine over time, is going to be equal to 1.0 times 10 to the -2 moles per liter per second. And so that is the answer for A. I'm going to move that one up here just a little bit because I know I'm going to run out of space. So let me just move that up here. So that's the answer to A. Now we're going to look at B. And in part B, it says, calculate the rate of appearance of HCl when the concentration of ICl is 0.15 and the concentration of H2 is equal to 0.20. So let's plug the numbers in here. Again, we know that our rate is measured as the rate of appearance of our iodine over time. I'm going to do this one a little more shorthand. So 1.63 times 10 to the minus 1, molar to the minus 1 times seconds to the minus 1. We have our concentrations, which are 0.15 molar and 0.20 molar. When you multiply all that spinach out in your calculator, you end up with 4.9 times 10 to the negative 3 moles per liter per second. And again, we know that that is equal to 1/2 I keep forgetting my delta. 1/2 delta HCl, the change in HCl over delta T. And if you're wondering, where did you get this from, Mr. Dion? This is something that we learned in the last class, right? We learned how to make an expression that relates the change in concentration of the products and the reactants to each other. And we learned that since the stoichiometric coefficient of the HCl is 2, we put 1/2. So now with that relationship, we can say that delta HCl over time, which is what we're looking for. We're looking for the rate of appearance of HCl, and that's this right here, is going to be equal to 2 times 4.9 times 10 to the minus 3 moles per liter per second. That's going to give us our rate, which is equal to 9.8 times 10 to the negative 3 moles per liter per second. And so that is the answer for part B. The last question, C, says, if the temperature of the reaction is raised to 100 degrees Celsius, will your previous answers be the same? Why or why not? Can anybody answer that question for me? If I change the temperature from 25 degrees Celsius to 100 degrees Celsius, will it be the same? Violet says no, and she's absolutely correct, right? No, the answers are not going to be the same because K, the rate constant, okay, rate constant changes with temperature. So remember, the rate constant is only constant at a specific temperature. If we change the temperature, walla walla bing bang, we have a new rate constant. All right, let's move on from that problem and take a look at another one. The best way to master the content in general chemistry 2 is by practicing it. This is the last question that we'll look at with respect to this section before we move on to talking about how we determine reaction order. Anyhow, it says this reaction 3A plus 2B gives you C as first order with respect to A and third order with respect to B. And the reaction is measured as the appearance of C. So that tells us what we know is that the reaction is measured as the rate of appearance of C over time, and it's equal to the rate constant times the concentration of A, its first order, times the concentration of B, and that is third order. And so this is overall what order? Could anybody tell me what order overall this reaction is? And it's not a trick question.
Fourth.
Absolutely. This is a fourth order reaction. So fourth order overall. I just added the exponents. Okay, well, let's take a look at A. It says, write the rate law. Well, we kind of already did that, didn't we? Anyhow, so we did that. And calculate the instantaneous rate of appearance of C when A is equal to 0.2 molar and B is equal to 0.05 molar. And it gives us the rate constant. So again, this is just a matter of plugging the numbers in. So I'm going to do this one kind of quickly. We get the delta, the change in concentration of C over time is going to be equal to 2.7 times 10 to the minus 1 moles to the minus 3 times seconds to the minus 1 times the concentration of A, which is 0.20 molar, times the concentration of B, which is 0.05 molar cubed. And that is going to equal 7 times 10 to the negative 6 moles per liter per second. That is our answer. Notice that we only have one sig fig because there's only one sig fig in this concentration. Now that's the answer to A. If we move on to B, It says calculate the instantaneous rate of B under the exact same conditions. Well, we know that from our reaction that you can see up here on the top, okay, that the change in concentration of C over time is going to be equal to negative the 1/2 of the concentration of B over time. And again, this is something that we looked at during the last semester. And so in order for us to calculate the change in concentration of B over time, we're going to have to take our change in concentration of C over time, which was 7 times 10 to the negative 6 moles per liter per second, and we're going to have to multiply that by -2, which is going to give us -1 times 10 to the negative 5 moles per liter per second. Now, if you're wondering why is it negative, the reason I'm leaving it as negative is because this is rate of disappearance, okay? Disappearance, because it is disappearing with time. All right, well, let's move on and address that question that a student had earlier on. The student said, if we have a rate law that looks something like, and this is just an example, if we go back to rate is equal to K times, concentration of X times concentration of B, concentration of A to the power of X times concentration of B to the power of Y. It's supposed to be the letter Y. It doesn't look like it, does it? Anyhow, how would we determine these exponents if we weren't given them? Well, the answer is that we would use what's called the method of initial rates, okay? And there's a couple of steps that you need to do to use the method of initial rates. So first, you set up a reaction. You choose the initial concentrations of both of the reactants, right? A and B. And you measure the instantaneous rate, or the initial rate, of both of those reactants, right? You know their concentrations, you measure their initial rates, okay? So you have a rate for each one of those reactants. Then what you do is you repeat the experiment. Now my diagram is kind of crappy going from here to here. What I was trying to get across is that B was changing, but A was staying the same, but it kind of looks like A moved anyhow. But the idea is that in your next experiment, you repeat the same experiment, except you change the concentration of one of the reactant and you hold the other one the exact same, okay? Then you compare the two reaction rates. Think about it. If one of the reactants concentrations didn't change, then that one is just going to cancel out when you compare the two reaction rates. Whereas the other one, you're going to be able to determine what kind of effect it had when you changed the concentration of that reactant. Now, the number of experiments you have to perform is going to depend on the number of reactants that you have. So until you determine the effect of the reaction, you determine their effect on the instantaneous rate for each reactant. Anyhow, so let's start with the simplest possible example. We got one reactant. Let me move this so you can see the whole question. It says, a student wishes to determine the rate law for this reaction. So what it's saying, like I'm stopping already, okay? We have a reaction. We know it's going to be something like rate is going to be equal to K times A, but we don't know what this exponent is. We want to determine that exponent. So what the student is going to do, he says, using the method of initial rates, the person is going to determine what X is. To do so, he measures the instantaneous rate of formation of B, okay? Son of a gun, I got to stop circling stuff so I can see the whole screen here. There we go. The instantaneous rate of formation of B, setting the concentration of A to 1, 2, and 3 molar respectively. This student is careful to keep the temperature constant during the whole reaction, and he gets this data. So it asks us to find the value of the rate constant K. All right, and we're asked to answer the question, why is the temperature maintained constant throughout the reaction? Well, I can answer B right away because we kind of already did that in a couple problems ago. And that's that K depends on temperature, doesn't it? Right? If we were to vary the temperature, then the K is going to change and then our experiments are no good. So the first thing that they're asking us is kind of funky because they're saying, can you just tell me what the rate constant is? What is K? Well, look, in my experiments, I have the concentration of A and I have the rate, right, which is measured as the rate of appearance of B over time. But the problem is I don't know what X is. So I need to figure out the reaction order in order for me to determine K. So must determine, okay, reaction order first. Okay, we got to do that. RXN, I use that as an abbreviation for reaction. So how are we going to do that? Well, using this generic rate law right here. Let me show you how we use the method of initial rates. And what I'm going to do is I'm going to compare reactions 2 or experiment 2 and experiment 1. I'm going to call this R1, or sorry, R2 and R1, since they're experiment 2 and 1 respectively. So if I compare the rate of reaction 2 over the rate of reaction 1, it's going to be equal to the K times the concentration of A in experiment 1 to the power of X, okay? So you can call this A1 times, and then R1, sorry, I meant to put RA2 over here. So experiment 1, I'm going to say R1 is equal to K times the concentration of A1 to the power of X. Let's plug in some numbers. So the rate of reaction 2 is 0.800 moles per liter per minute. The rate of reaction 1 is 0.025 moles per liter per minute. Okay, they're both equal to K. Okay, we got that K here. The concentration of A in reaction 2 is 2 molar. So we'll put that in 2.0 molar to the power of X. And the concentration in the first one is 1.0 molar to the power of X. Look what happens when we divide these. These units cancel. Moles per liter per minute cancel. The K cancels. The molar cancels. So all I'm left with are the numbers, right? If you take 0.8 and you divide it by 0.025, you get 32 is equal to 2 to the power of X. Now, how do we solve for X? Well, you could just do it in your head and say 2 to the power of 5 gives you 32. Or you could solve it using logs, right? You could take the log of both sides. You could say the log of 32 is equal to X times the log of 2. So that means that X is going to be equal to the log of 32 divided by the log of 2. So that means that X is going to be equal to 5. So that means that our reaction is fifth order. So now we know that our rate, okay, which is equal to the rate of appearance of B over time is equal to K times A to the power of 5. So now that we have that, and we have 3 experiments, we can determine our K, can't we? Right? So let's do that. We're going to use, I'm just looking at my notes here. I think, I don't know, find the value of the rate constant. Let's just use experiment 1. So we'll use experiment 1, and then we're going to say that rate is equal to K times the concentration of A to the power of 5. So that means that K is going to be equal to rate divided by A to the power of 5, like that. So our K is going to be equal to 0.025 moles per liter per minute, okay, divided by A, which is 1.0 to the power of 5. So that, oh, I left my units out, didn't I? There we go. So it's going to be molar to the power of 5. So molar to the power of 5. And when we work that out, let me grab my calculator, put it away when I need it. Where's my... There it is. My kids come down to my office and they think that the calculator is just the most interesting thing ever. Oh, I don't need a calculator. I get 0.025. If I have molar to the 1 and molar to the 5 in the denominator, it's going to be molar to the minus 4 times molar minute to the minus 1. And that is the value of my K. And we already answered question B, which is that K varies with temperature. So there we go. So that's the method of initial rates. Who wants to try another problem where we get to determine the rate law for reactions? Anybody want to try another one? I say yes. Okay. let's give this one a try here. Is anybody with me? All right. Yes, please. All right. Okay. So let's get going here. Here's another one. We're going to use the method of initial rates. It says here, for this reaction, D plus 2E gives you F. Use the following experimental data to find the rate law, the rate constant, and the instantaneous rate of appearance of E when you have these two concentrations. So there's a lot to do here. All right, we might just do the first two parts because you guys, we've looked at part C like 3 times already in this class. So we know that the rate law is going to look something like this. Rate is going to be equal to K times the concentration of D to the power of X times E to the concentration of E to the power of Y. Okay, so if we want to determine, let's start by determining X. So what are we going to do? If we want to determine X, we need to choose the two experiments to compare where the concentration of E remained constant. So that way we would be able to eliminate E when we compare the two. So I'm going to take reaction 3, okay, and I'm going to divide it by reaction 2, or rate 3 divided by rate 2. And since this is our rate law right here, okay, so rate 3 is going to be equal to K times D, which is 0.74 molar, okay, to the power of X, times E, which is 0.63 molar to the power of Y. Then I divide that by, how do I get rid of that select all thing? There we go. K, in experiment 2, the concentration of D is 0.37 molar to the power of X times 0.63 molar to the power of Y. So look what cancels. All of this is going to cancel. And this is going to cancel. So then let's plug in some numbers. So we get 0.018 moles per liter per second divided by 0.009 moles per liter per second, okay, is equal to 0.74 molar to the power of X divided by 0.37 molar to the power of X. I should have mentioned that molar cancels too. This molar cancels. Okay, so then when we plug in our numbers, okay, so now I'm going to do the calculation. 0.018 divided by 0.009, that equals 2. It's going to be equal to 2 to the power of X. We don't need to do any logarithms here. Can anybody tell me what X is equal to? It's not a trick question. What would X be? 2 to the power of what gives you 2? 1. Exactly. So that means the reaction is first order with respect to D. So we got that part done. Now we're going to do a comparison between two other reactions, right? If we want to get Y, okay, if we want to know what Y is, we have to choose the two reactions where the concentration of D remains constant so we can eliminate it. So I'm going to do this one a little bit quicker, and we're going to divide R1, the rate of 1, rate 1, divided by rate law 2. So that's going to be equal to 0.036 moles per liter per second divided by 0.009 moles per liter per second is equal to K times, I'm just going to use rounded brackets because square ones are just so hard to do, times 0.37 to the X. Now, if you're like Mr. Dion, you already know that X is 1. Why don't you put the 1 in? I just want to eliminate it, okay? I'll just leave the X. If you want to put a 1 in, be my guest. It'll still cancel. It doesn't matter, okay? Times 1.26 to the power, sorry, I left my concentration out. 1.26 molar to the power of Y divided by K. And we have 0.37 molar to the power of X. And we have what? 0.63 molar to the power of Y. Look at what cancels out. This isn't magic. Look, this is going to cancel. All this is going to cancel. Molar cancels. And when we simplify that, okay, if you take 0.036 and you divide it by 0.009, what do you get? 4. If you take 1.26 and you divide it by 0.63, you get something very close to 2. So that's going to be equal to the power of Y. It doesn't take a genius to know that Y is equal to 2. 2 squared is 4. There you go. Now we figured out both X and Y using the method of initial rates. So we know that our rate law is the rate, okay, which is measured as the instantaneous, the rate of instantaneous appearance of F, so which is delta concentration of F over delta T is equal to K times D to the power of 1 times E to the power of 2. So there you go. There's our rate law, ladies and gentlemen. Okay? And if we wanted to determine the K, we could use any one of these experiments. I don't have a lot of space left here, so I'm going to kind of make some space here. So we'll use experiment 1, okay? And we're going to say that K is going to be equal to rate divided by D, concentration of D, times the concentration of E to the power of 2. So plugging in the numbers, which would be 0.036 moles per liter per second, divided by 0.37 molar and 1.26 molar squared. When you work all that spinach out, you end up with a K, which is equal to 6.1 times 10 to the negative 2 molar to the minus 2 seconds to the minus 1. And there you have it, my friends. That's it. We determined the K. And then for C, I'll just say C, no pun intended. I will say, see previous questions, okay? Because we already looked at several examples where we had to do the exact same thing. All right. Brogan asks, what if you don't have E being a constant? Can you still find X? No. The answer is no. So I'll always give you enough experimental data that you will be able to determine the exponents. All right. So as I told you on the first day of class, I provided a lot of practice problems, so many practice problems that there's no way we will be able to work through all of them in time. But this is another practice problem where you're doing the exact same thing, the method of initial rates. The only difference is with this problem, you have to do that same exercise 3 times. So this is a really good practice. The rate here is going to be equal to the rate constant times the concentration of H2SeO3 to the power of X times the concentration of I minus to the Y times the concentration of H plus to the power of Z. And so you can use all this experimental data, and Brogan, trust me, there's enough data in here to solve for each one of these exponents. And again, I have the solutions to this problem posted on Canvas. I'm just going to back up and say one more thing about the method of initial rates, okay, before we look at one quick problem before we finish. And if you look at the examples that are in our textbook when they solve these kind of problems using the method of initial rates, you'll see that they don't even do, or oftentimes they don't even do anything like this. They don't even show you the numbers. They just say by inspection. So just by looking at the numbers in the table, they just do it in their head. Okay, so after a while, you kind of get pretty quick at it, and you say, well, if I take 1.26 divided by 0.6, it's about 2, and then I get 4. So yeah, it's going to be, y would be equal to 2. So what you're going to find is as you progress in the class, you'll be able to solve a lot of these problems in your noggin. Okay, let's take a look at one last one. This is kind of an interesting one. This deals with something that's a zero order reaction. And let me show you what we mean by a zero order reaction. It says that you have N2O decomposing on the surface of a gold catalyst. It's kind of an interesting place for a reaction, isn't it? On the surface of a solid, because we know that gold is a solid. We know that our rate law should look something like rate is equal to K times the concentration of N2O to the power of X, okay? To the power of X. But if we use the method of initial rates, let's compare experiment 1 and experiment 2, because you see the concentration of N2O varies, okay? Let's compare those. So if we take R1 over R2, we see that 0.005 moles per liter per second is over 0.05 moles per liter per second is equal to K. And in the first experiment, my concentration of N2O was 1.0 molar to the X, and here it's K times 0.5 molar to the power of X. Look at everything that cancels here, right? We have K we have molarity, we have moles per liter per second. But then we get what? When we simplify this, we end up with 1 as being equal to 0.5 to the power of x. That means that x is equal to 0. So this is a 0 order reaction. Okay, a 0 order reaction. Now, it even tells us that in the second part. In B, you notice that I wrote the rate law for the above is, rate is equal to K, right? Because if it's 0 order, if you have rate is equal to K times N2O to the power of 0, well, that cancels and gives you 1. So that means that rate is simply equal to K. Well, if you have a 0 order reaction, it says, how is this possible? You could read this in the textbook. It goes into a little bit of detail about what a 0 order reaction is. It says, well, what we're looking at are actually what are called pseudo 0 order reactions, because you think, what if you had 0 concentration? You mean the rate is still going to be the same if you had nothing? Well, that's kind of what it would look like here, wouldn't it, right? Anyhow, but the idea is the reason why this is possible is because the reaction takes place on a solid. Takes place on, not of, but on a solid surface. And that's the only time we can have a 0 order reaction. All right, well, let's move on from there. Give me a thumbs up if you're like, I think I understand this a little more, but I might need to go back and do this question here and some other practice problems. Okay, I can't stress this enough, okay? I know I sound like I don't want to come off sounding like a dad, but I am a dad. And so I highly recommend reading the book before coming to class and giving it a try yourself before coming to class. General Chemistry 2 is a challenging class, okay? I never said it was going to be an easy class, It's not just like General Chemistry 1, these are the elements, add up, 1 plus 1 is 16, gives you 18, that's the molar mass of water. This class is a lot more involved, so it's going to require a lot of practice before you step into the examination room. All right, well, let's move on. So far, we've been talking about rate laws, right? We spent the whole day so far, up until now, talking about rate laws, and that we can measure the instantaneous rate of a reaction when we know the concentration of the reactants, okay? But what we're going to look at now is what's called an integrated rate law. And an integrated rate law is different. We're not talking about the rate with measuring the rate with respect to the concentration. We're going to measure concentration or change in concentration of reactant over the course of time, okay? And so we have something called an integrated rate law. And it says here, the integrated rate law is used to express the change in reactant concentration over time. And we're only going to look at reactions that involve one reactant. So one reactant only. And when it comes to integrated rate laws, we're only going to look at 0, first, and second order reactions. So we keep things really simple, because I know when a lot of students see the word integration, right, they know that it's calculus and they're like, I'm not so sure about that. But don't stress about it. So here's where I am, okay? It says consider a reaction where we have A gives you products. The rate of this reaction is measured as the rate of disappearance of A. Using the method of initial rates, we can determine the rate law for the rate of disappearance of A. So the rate of the disappearance of A, oops, that's kind of an ugly square bracket, isn't it? The rate of disappearance of A over time, okay, is equal to K times the concentration of A to the power of X. Now, again, the instantaneous rate of reaction, I talked about this briefly during our first lecture. I said, that's the rate of reaction when the change in time approaches 0. And in order for us to do that, we have to take the first derivative of a concentration versus time constant. We are not going to be doing any derivatives in this class, okay? In case you're worried, look right here. It says integration techniques are not learned in Chemistry 1411. You don't have to have calculus to take this class. And so we will provide the integrated rate law for 0, first, and second order reactions, okay? For a simple reaction, A giving you products, okay, we're going to provide those for you, okay? So when we integrate those rate laws, we get the integrated rate law. And let me show you what an integrated rate law would look like if we were to have a zero order reaction. Okay, so if we have a zero order reaction, we have this reaction right here. This is the reaction we're talking about. If that reaction is zero order, then we know that our rate law is simply rate is equal to K, right? We saw that already today. And we know that our rate is measured as the rate of disappearance of A over time. So you could just say rate is equal to this, which is also equal to K, okay? If we integrate this rate law, okay, and again, I'm not going to ask you to do that. If you go on Canvas, you can see that I've even published the not cheat sheet, what do you call it? I don't know, assistance sheet, anyhow, the handout for the first exam. It's already on there. So if you integrate a zero order reaction and get this integrated rate law, which you can use to relate the change in concentration, the change in concentration of the reactant over time, it's concentration of A is equal to negative times the rate constant times time plus the original concentration or the initial concentration. So remember that A0 here, that's the initial concentration of A. What do you notice about that equation? It's kind of cool, huh? It takes on the exact same form. Sorry, I'm trying to find my eraser here. There we go. It takes on the exact same form of y is equal to mx plus b, doesn't it? In fact, if you were to make a plot, right, and our x-axis is going to be time, our y-axis would be concentration of A. What you would see is that you would get a negative slope, right, because our slope, which is our m, is negative. You'd get a negative slope, so this would be negative k, because our rate constant is going to be positive. And the y-intercept would be the initial concentration of A. Kind of cool, huh? So again, I'm not going to ask you to produce this equation, but you'll have to be able to recognize it. Okay, you'll have to be able to recognize it. All right, anyhow, so there's the integrated rate law for a zero order reaction. With that in mind, let's give it the old college trial. Let's do one for Clyde, and let's see if we can solve a problem here. It says if K, the rate constant, is equal to 5.00 times 10 to the minus 3 moles per liter per second for a zero order reaction, A is giving us products, what concentration of A is present after 60 seconds if the concentration of A at the start of the reaction was 1.00 molar and rate is measured as the disappearance of A over time? Well, we have our integrated rate law, which is the concentration of A is equal to negative rate constant times time plus the initial concentration of A. What are we solving for? All we're doing is we're solving for the concentration of A after the 60 seconds. So the concentration of A is going to be equal to negative of the rate constant times time, which is 60 seconds, plus the initial concentration, which is 1.00 molar. You notice that seconds and seconds cancel. I should only have 2 sig figs here because I have 2 sig figs in 60, and that gives me concentration of A is equal to negative 0.30 molar plus 1.00 molar. You take 1 and you add negative 3 to it, what do you get? 0.70 molar. And so after 60 seconds, that is the concentration of A, because the concentration is going to decrease over time. So the take-home messages from this slide are, this is the integrated rate law that's highlighted in blue. I have it written in the form y equals mx plus b. If you were to graph this, you would end up with a straight line with a negative slope, which is the rate constant, and the y-intercept would be the initial concentration of A. Give me a thumbs up if you had the integrated rate law. I don't ask you to memorize it, but if you had it, you could solve this problem, just plugging in some numbers. Give me a, all right, Sanam, thank you. And Violet, I'll take it. Let's move on from there. Okay, and let's take a look at a first order integrated rate law. All right, same kind of thing. If we have just our good old simple reaction, A going to products, it's the only kind of integrated reaction that we're going to look at integrated rate laws for. Once you get two reactants, it gets a lot more complex. So don't worry about that. That's another class, okay? What if it's a first order reaction? Well, in that case, the rate law would be rate is equal to the rate constant times the concentration of A to the power of 1. We leave it out. When you integrate that rate law, you get this integrated rate law right here. The ln, the natural logarithm of the initial concentration of A, subtract the ln of the concentration of A is equal to the rate constant times T. There are many ways that you could express this, right? You could rearrange this a bunch of different ways. Now, I like to write these down in the form of y equals mx plus b. So I'm going to take this equation and I'm going to write it down in the form of y is equal to mx plus b. And it's going to look like this. The ln of A, concentration of A, is going to be equal to negative kT plus the ln of the concentration of A. This is the form y is equal to mx plus b. So that means if we were to graph this, should fix my x-axis up, shouldn't I? Try again here. There we go. So that means that our x-axis would be t. Our y-axis would be the ln of the concentration of A. Our slope would be k, and it's a negative slope. So this would be negative k. Oh, I should have moved the ln. So this is the y-intercept up here. Anyhow, and then down here, this is the ln of concentration of A. And if you're wondering about these graphs, I do have them on another slide. But of course, you know that because you were reading the slides with bated breath ever since Wednesday. But anyhow, you would get a graph that looks something like this. Anyhow, another way that you could rearrange this formula here, the ln of AO divided by A is equal to KT, that's useful in some instances. But if you flip those over so that it's the ln of the concentration of A divided by the concentration of A original, that's equal to negative KT, and that's actually more useful. And I think that's how they express it, or they actually have both of these in their textbook. You know, they show how to manipulate it. But, you know, and I'm probably not going to say this very many times moving forward because I've said it quite a bit, but you need to be kind of Johnny on the spot with your algebra, and you need to know what natural logarithms are and logs and things like that, and know how to rearrange equations in order to get through general chemistry too. All right, so now that we have the integrated rate law, I've written it down here in a bunch of different forms. And anyhow, so take your pick, whichever one you want to use. Let's try a problem. It says the following reaction is first order with respect to N2O5, dinitrogen pentoxide. The value of K is provided, 1 times 10 to the minus 3 reciprocal minutes, and the initial concentration of dinitrogen pentoxide is 1 molar. Calculate the concentration of dinitrogen pentoxide after 100 minutes. So let's see here. If we have, I'm going to use my favorite form, which is the y equals mx plus b form right here. So if we have that form, if we have the ln of the concentration of A is equal to negative KT plus the ln of the concentration of A that we start out with. If we take the natural logarithm of both sides, we would get that A is equal to E to the power of negative KT plus the ln of the original concentration of A. So we're taking all of this and we're putting it to the power of E like that. So now we're just going to plug in some numbers. So we're going to get that E is equal to negative 1.00 times 10 to the minus 3 reciprocal minutes like that times 100 minutes like that plus the ln of 1, which is 0. So there we go. All right. So there we go. Anyhow, when we put all that spinach into our calculator, we end up with E to the power of negative 0.100. So that means that our concentration of our N2O5, okay, which I could have put in here, I just didn't, okay, is going to be equal to, what is it, 0.905 molar, like that. So there's the concentration after time. Now, the second part of this question asks us to calculate the rate of disappearance of N2O5 initially and at 100 minutes. So if we want to measure, let me just make some room here. Maybe we'll just do one of these since I don't have a ton of room. Why don't we do it at t is equal to 0 first? Now, since this is a first order reaction, we have that the rate of disappearance of N2O5 over time is going to be equal to our rate constant times the concentration of N2O5, like that. So that's going to be equal to our K, which is 1.00 times 10 to the minus 3 minutes to the minus 1, okay, multiplied by 1.00 molar. This is at T is equal to 0. So at T is equal to 0 minutes. And when you multiply all that out, you get, what do you get? 1.00, well, same thing, times 10 to the negative 3 reciprocal minutes, okay? So that's at time is equal to 100 minutes. If we wanted to do it at 0 minutes, we would do, oh, did I do it at, no, sorry, that's T is equal to 0. At T is equal to 100 minutes, so this is the concentration at T is equal to 100 minutes. Sorry, I'm having a hard time reading my writing here. I made some notes about this. Anyhow, then you would get that the rate, okay, it's going to be equal to, what is it? 1.00 times 10 to the minus 3 reciprocal minutes multiplied by 0.905 molar. And when you punch that spinach in your calculator, you end up with 9.05 times 10 to the minus 4 moles per liter per minute, like that. All right, there we go. So that's a first order integrated rate law. And then last, we're going to look at the second order integrated rate law. So we're doing the exact same thing. Again, I don't expect you to integrate the rate law yourself. Not at all do I expect you to do that. But look what happens when we take our reaction. And look, if you're not following me, if you're a little bit lost, just stop for a second. Let's take a deep breath. Okay, what are we looking at? Okay, I'm going to kind of review here for anybody who's not following me 100%. All we've been talking about since I started section 12.4 is I'm only talking about this reaction. A gives you products. And then we're talking about reaction order. If the reaction is 0 order, we looked at the integrated rate law. If the reaction order is first, we looked at the integrated rate law. Now, if it's the second order, that would be the rate law, wouldn't it? Right? We've looked at that already. If you integrate that, you end up with this equation. I do not ask you to do the integration yourself, okay? I will provide this for you. Okay, now somebody wrote in the comments, they said it's super helpful to see it in the y equals mx plus b form. We're friends because I couldn't agree more. That's my favorite form. It's the easiest way to understand what the hell is going on. Let's take this formula that's highlighted in blue and let's rearrange it to y equals mx plus b form. This is how we would do it. We would say that 1 over the concentration of A is going to be equal to KT plus 1 over the concentration of the original concentration of A. So if we were to plot that on a graph, our x-axis is always T, but in this case, our y-axis would actually be 1 over the concentration of A. Now we would have a positive slope, which is going to be equal to K, and our y-intercept would be 1 over the concentration of, or sorry, the original concentration of A. So y equals mx plus b form. I couldn't agree more. It's so helpful. It's so helpful. And I'm going to ask you some questions on your first exam about, your understanding of this too. Like, do you understand the y equals mx plus b form? The book goes over in gross and dirty detail. But with this integrated rate law, let's see if we can solve a quick problem here. It says you have a second order reaction, right? The only kind of reaction that we're looking at. Look, remember people, okay? we are never going to look at integrated rate laws for something like this, okay, where you have two reactants. Way beyond the scope of our class. Gets quite a bit more complex, okay? So only the simplest possible reactions are we going to look at, and only for zero, first, and second order. We're already on second order. We did the first two, so let's do this problem, okay? We have a second order reaction, and it says, how many minutes does it take for the concentration of A to decrease by 7.00 times 10 to the minus 3 molar when the initial concentration of A is 4.02 decrease? I don't think I did this question the right way now that I look at my notes. Let me just double check here. I'm going to change the wording a little bit here then. Just give me a second here. Anyhow, the initial concentration is 4 times 10 to the minus 2, and here's our K. So I'm going to change the wording to, instead of decrease by, I'm going to have it decrease to. Okay, it's just going to decrease to this concentration. I forget in my solutions whether I did it decrease by or decrease to, but the solutions are posted to Canvas. So the solution for every one of the problems in this slide deck, or at least I think all of them, are found posted to Canvas. So look, we have our integrated rate law. I'm going to use the form y equals mx plus b. It's my favorite form. So we have 1 over the concentration of A is equal to K times T plus 1 over the concentration of the original concentration. We are asked to solve for T, right? We're looking for T. So let's do that. Let's rearrange the formula to solve for T. And when we do that, T is going to be equal to 1 over the concentration of A, subtract 1 over the initial concentration of A, divided by K. So we get that our T is going to be equal to 1 over 4.00 times 10 to the negative 2 molar, subtract 1 over 7.00 times 10 to the negative 3 molar, divided by our K, and our K is 0.622 moles per liter reciprocal per minute. Oops, I don't know what that is. Anyhow, when you punch that in your calculator and you simplify it a little bit, you get 30.3 molar subtract 25.0 molar divided by 0.622 reciprocal molar per minute. Like that. Sorry, these are reciprocal molar. I was like, why doesn't that cancel? There we go. Oops, I didn't mean to do that. Where am I? By the way, I don't even know anybody named Ellen. That's a friend of my wife. Anyhow, where was I? Okay, so you can see that reciprocal molar cancels. And since we have minutes to the minus 1 down here, we end up with a T that is equal to 8.52 minutes. There we go, my friends. So now you've seen the zero, the first, and the second order rate laws. Give me a thumbs up if you're like, yeah, I think I'm kind of following this a little bit. I'm going to need to practice it. And be sure that when you're practicing, be sure that you look at the handout that I will provide you. Okay, I'm going to provide you with a handout for the exam, and so make sure that you use that when you're studying. All right. So I'm going to give you the y equals mx plus b form. However, I will not tell you which rate law you're looking at. So make sure that you look at the handout. Violet, I think you're right. I'm going to have to go back and take a look at this, and I'll address it on Friday. So somewhere I punched in something wrong, but in the interest of time, I just want to keep moving forward. And again, the solution is posted to Canvas, but we'll come back to that on Friday, and we'll take another quick look at it. But the thing I wanted to get through today was I wanted us to take a look at half-life. So the half-life of a zero-order reaction, a first-order reaction, and a second-order reaction. So what is a half-life? You might be wondering, what the hell is a half-life? Well, the half-life of a reaction is, I think, kind of intuitive. It's the amount of time that it takes for half of your reaction to disappear, right? You start with, say, 1 gram of something. Well, how long does it take before it decomposes to half a gram, right? You start with 2 grams. How long does it take for it to decompose to 1 gram? So that's what a half-life is. Now, we can derive an expression for half-life by substituting in this, that the concentration of A at T1/2 is going to be the initial concentration divided by 2. If we plug that into the rate law, then we're going to end up solving T for the half-life, sorry. Let me show you what I mean. It says here, derive the expression for half-life of a zero-order reaction of this form. Now, we've already looked at the y equals mx plus b form of a zero-order reaction, so we know that a zero-order integrated rate law is going to look like A is equal to negative KT plus A, the initial concentration of A. So what we're going to do is we're going to replace the initial concentration, we're going to replace the concentration of A with the initial concentration divided by 2, right? Because at half-life, the concentration of A is equal to the concentration of the original concentration divided by 2. So let's do that. When we plug in some numbers here, we put the concentration, the initial concentration divided by 2 is equal to negative KT plus the initial concentration. All right, that means that KT is going to be equal to the initial concentration divided by 2, which means that T, which is equal to T1/2, the half-life, is going to be equal to the initial concentration divided by 2 times the rate constant. And there's our expression for a half-life for a zero-order reaction. You should be able to do this, okay, on an exam. If you see this equation, you should say, okay, well, I know that's a zero-order integrated rate law. If I need to calculate the half-life, I'm just going to substitute in the initial concentration divided by 2 for the concentration at the half-life, and you should be able to derive this equation. Let's do the exact same exercise for a first-order and a second-order rate law. So let's try it for a first-order reaction. We do the exact same thing. It says derive the expression of a half-life for a first-order reaction. Well, let's start with the first-order integrated rate law. The form that I'm using, and again, you can use whatever form that you want, but I'm going to use this one, and this one was on the slides, which is the ln of the concentration, the initial concentration of A divided by the concentration of A is equal to KT, okay? Again, you can use any of the ones that are on our slides for first order, but we're going to use this one, and we know that at half-life, the concentration of A is going to be equal to the initial concentration divided by 2. So let's plug in some numbers. We get the ln of the concentration of A at the start is divided by the initial concentration divided by 2 is equal to K times T. Okay, we see that these are going to cancel, and we end up with the ln of 2 is going to be equal to K times T. Therefore, T, which is equal to the half-life, is going to be equal to the ln of 2 divided by K. And there you go. We did it. We derived the half-life expression for a first-order reaction. Now let's do the same thing for a second order. Okay, we're doing the exact same thing again, but we have a different integrated rate law this time. So for a second order reaction, or a second order integrated rate law, we have 1 over the concentration of A is going to be, or subtract the concentration at the start is equal to KT. And at half-life, we know that the concentration of A is going to be equal to the initial concentration divided by 2. Let's plug in some numbers. So we get 2 over the initial concentration of A, subtract 1 over the initial concentration of A is equal to KT. That means that 1 over the initial concentration of A is equal to K times T. And we know that T is equal to a half-life. Okay, so it's going to be equal to 1 over the initial concentration times K. And there you have it, my friends. We've just derived the last one. So now we've derived all the rate laws, or sorry, the half-lives for first, 0, and second order reactions. All right, there we go. So in summary, this is kind of what we've covered today. We looked at 0, first, and second order reactions. We looked at a very simple reaction, just A giving us the products, and then we looked at the integrated rate laws for all of these. Here are the integrated rate laws. Here's the plot that you need for a linear fit of the rate data. Here's the relationship between slope and the linear plot. So you see that in the first two that the slope is negative, and in the last one it's positive. And we just derived all of these expressions here. So we did all of that just today. So that's a summary. All right. So somebody says, we'll add more than 6 pages of scratch paper. Yeah. You needed to be able to derive the half-life working. Well, of course you can memorize it. I'm not going to stop you from memorizing anything, okay? You can memorize the entire textbook and the whole solutions manual if you want to, but you have to be able to derive it. Somebody has a question about a first order. So I'm just going to stop there and just go back here.